Who can tell me what it means for a function to be even?
Function.
Yes. Close. Go on. You didn't even know what he said. What did he say? Well, yeah. All the exponents are even. That's right. And what did that mean for our functions? Anybody remember what even functions did? Yeah. That's right. Yes. They were symmetrical around the y-axis. In the next few days, we're going to be finding more and more roots of functions and things like that. Well, here's the problem. I'm going to be giving you problems like this one. Here's why that's going to be helpful to know. I'm going to give you problems like this one. F of x, now this is just an example, so you don't have to write this down. X to the fourth minus x squared plus 16 or something. Something like that. Now, how many roots should that thing have? 4. Right, same as the degree. Well, I'm going to be asking you to find all 4. Well, the beauty of even functions is because they're symmetrical, you know that for every negative root, there's a positive root, and vice versa. So, like if positive 2 ended up being the 0 of that thing, negative 2 would be as well. If positive 4 would be, negative 4 would be. Even functions, because they are symmetrical, if you find a negative or positive number that is a root for that function, then its opposite will be as well. So for every 1 you find, you've actually found 2. So that's going to be something very helpful to you as we move on. You may not have to use it today, but it will be very useful very soon. So today, we're going to be picking up where we left off on Friday, where, if you remember, the last few problems you had on Friday's homework were, here's a polynomial. Here's one of the roots. Take it out and find the other roots. Then you took synthetic division, you pulled that root out of it, and then you did the quadratic equation. Right, that's what we did. I know it was a long time ago, so just take my word for it. Well, today I'm not going to give you any of those. You're going to have to find a root to take out. And you're going to do that using the rational zero theorem. The rational zero theorem simply states, let me put it like this. This is 2.5. Let's take a look at this problem. Now, if I ask somebody to factor that, don't tell me what the factors would be. How would you start looking for the factors? Someone who likes to factor, in fact, somebody I'm sure already knows this. So if you want, tell me what the factors would be and I'll ask you how you got it. Yeah. That's right. X plus 2, X plus 3. How did you know 2 and 3? That's right. 2 numbers that multiply to get this, right? 2 factors of 6. That same principle applies for all polynomials. Now, it's just not quite as simple because there's more terms in the middle. So, the rational zero theorem, based on that exact same principle, says this. Sometimes zeros of a function won't be very pretty, like 0.27156. But if they are going to be pretty, or if they are going to be rational, which simply means that you can write it very easily as a fraction, then they are going to be of the form P over Q. What does that mean? Good question. I'll show you. Let's look at number 3. The last number is your P value. The first number is your Q value. First thing you're going to do on 1 through 8, and this is all you have to do, is list your P's and Q's. So just like Houston found the factors of 6, we are going to find all the factors of 6. What numbers multiply to get to 6? 1, 2, 3, and 6, positive or negative. What are all the numbers that multiply to get Q? Plus or minus 1 and 3. So the rational root theorem says, if you're going to have a zero to this function, that's going to be a nice, pretty, either a whole number or a simple fraction, it's going to be of some form P over Q. So all you have to do are take all your P values and divide them by all your Q values. So, plus or minus, 1 over 1, 2 over 1, 3 over 1, 6 over 1. Now we go to the next one. 1 over 3, 2 over 3, 3 over 3, which is just 1, and 6 over 3, which is just 2. So I'm not going to bother writing them. So that says, if there are going to be zeros of this function that are easier than the others to find, they're going to be in this list. They're going to be in this list. And that's all you have to do for these problems is list those. If you have a rational zero, it'll be one of these. Yeah, the factors of P and the factors of Q. And then you just all the P's on top of all the Q's. Now, some of them, I'm not going to lie, you are going to have some in the future, maybe not today, but that can get a little lengthy. It'll be something like, I'm just going to make this one up, because this is the hardest possible example I could possibly think of for this. Let's say you had one, I'm going to make up number 8. This isn't the real number 8, but let's say it was 12x to the 6. Who cares about what's in the middle, because all we care about is the last few terms, minus 36 or something. Now your p-values are going to be plus or minus 1, 2, 3, 4, 6, 9, 12, 18, and 36. Yeah, they can get a little lengthy. Your q-values will be plus or minus 1, 2, 3, 4, 6, and 12. And now when you list all your p's over q's, you can see with all possible combinations, that can get a tad lengthy. Yes, that's the case. Sometimes that's just the way it is. Most of the ones you have today will be something like this or shorter. But it is possible for them to get rather extended like that. Let's look at number 7. Number 7. What are my p-values? Plus or minus 1, 2, 3, 4, 6, and 12. All the factors of 12. What are my q values? That's right. It's just the leading coefficient of 1. Those are nice. When your leading coefficient is 1, that's awesome because that basically means your p values are your p over q. There's not much you have left to do. Your p over q are your p's. So for those problems, you don't even have to list your p's and q's if you don't want to. I think it's easier if you do. But all I really need to see is your finished p over q list for 1 through 8. All I need to see. Now, who thinks they can predict what the next slide is going to be? If we're finding potential zeros, what makes the next logical point? What are these? What's the point of finding these? You can tell me that. Yeah, plug them in and see which ones work, right? The next slide that we're about to deal with, we're going to find this list. Then, from that list, we're going to find 1 or 2 of them that actually work, that actually are zeros of the function. And we're going to divide them out and finish finding all of the zeros. So, 9 through 15, we're going to list our p over q's. We're going to use synthetic division or the rational or the zero remainder theorem from last section to find which ones actually work, and then we're going to divide those out and find all of our zeros. That may sound like a lot, but it's really not so bad. Let's look at it. Let's look at number 11. Number 11. Okay, now, the key to all of these is to try to get them down to a quadratic. Factor out as many factors as you can to get down to a quadratic, and then finish it up with a quadratic equation. What are my p's and q's? What are my p-values on number 11? 1, 2, 3, and 6. What are my q-values? 1 and 2. Very good. Now, my p over q's are going to be 1, 2, 3, 6, plus or minus. And then 1/2, 3/2, and 2/2 and 6/2 are already on the list. Questions about where that's coming from? Yes. Now, not all of these are going to work. In fact, at most, only 3 of them will work. At most. We're just hoping to find 1 to start out with. Now, you can find to see if they are actual zeros. You can do it one of 2 ways. You can just plug them in. Remember that one set of problems we did in the last homework? The whole thing was about how it's the same thing if you plug in or if you synthetic. You can just plug them in, but without the use of a calculator, that might be a tad difficult. Or you can use synthetic division. Synthetic division, once you get good at it, it's actually really, really quick. To start out, just to show you that you can plug them in, I'll start by plugging in positive and negative 1 and seeing if either of those work. If I plug positive 1 into my function, I get, now what am I hoping this equals? Very good. So, if I plug in positive 1, that's 2 minus 3 minus 11 plus 6. Is that going to equal 0? No, it's negative 1, negative 12, positive 6, or negative 6. Not 0. So positive 1 did not work. Let's try negative 1. So it'll be negative 2 minus 3 plus 11. Is that going to be 0? No. Now, when you get to plugging in anything bigger than that, it can get a little lengthier because you're going to have to cube things. So I actually believe it's easier to use synthetic division. Let's see if 2 is a 0 of this function. So, synthetic division, just like the other day. Drop the first term, multiply, add, multiply, add, multiply, add. Was 2 a 0 of this function? No. So I'm going to try negative 2. Multiply, add, multiply, add. Hot diggity, we found one. That, negative 2, is a 0 of our function. Now I'll stop for a minute, let you all get caught up, and let you ask any questions you have about what we've done so far. Well, you just need to find one. Yeah, you try positive and negative, and you just keep trying. 1, negative 1, 2, negative 2, until you find one that works. Sometimes you'll get all the way to the last one until you find one. Well, I'm going to explain that in just a second. Here's the thing. Would you agree that this, if we did this for every single possible one, that would get a little tedious, right? Remember, dividing is the same thing as factoring. If negative 2 is a 0, then what's the factor that would have given us negative 2? X plus 2. We've essentially just factored this into this. By finding out that negative 2 is a root, we have essentially factored x plus 2 out of our original and gotten down to this. 2x squared minus 7x plus 3. Now, to answer your question, Jenny, yes, I want you to find all three of them. But you don't have to keep doing that. Because you're now down to a quadratic. And what can we use on all quadratic functions? The quadratic formula. And you can always tell by the degree how many you're going to need to find. We only needed to find 1 here to get it down to a quadratic. If this had been to the 4th, we would have needed to find 2 to get it down to a quadratic. We'll deal with that in a second. All right, so quadratic formula. Negative b plus or minus b squared minus 4ac all over 2a. That's just this function here in the quadratic formula. 7 plus or minus 49 minus 24. Ooh, that's 25. That's a perfect square. When you finish the quadratic formula, 7 plus 5 is 12. 12 over 4 is what? 7 minus 5 is 2. 2 over 4. And I want you to list all three of them. What was our original one? Negative 2. And here's your finished product. You have found all three roots of this function. And notice, all three of those are nice numbers, and all three of them were on our list. So you could have found all three like that. But oftentimes they won't be. You'll get like negative 2 and then either two imaginary numbers or like 1 plus or minus radical 7, stuff that's ugly. So that's why the safest bet is to just do the quadratic. And that's it. You're done. You find one, take it out, quadratic. Yes, of course. No, I'm not a big Doctor Whoer. Questions? Now, I want you to look at something. Look at these directions. Look at these directions. Now look at the next slide. Notice 9 through 16 and then 17 through 24. These are different sets of directions. What's the difference in the directions? What? Yeah, the only one word difference in those two sets of directions. Zeros, that's right, and roots. Just trying to reinforce that those two words mean the exact same thing. We're doing the exact same thing on this function. Let's look at 23. 23 is a little different because I can't just find 1 and take it out because I won't be down to a quadratic. How many do I need to find on 23? 2. I need to find 2. That way when I take them out, I'll get down to a quadratic equation and be able to use the quadratic formula. So, here we go. What are my p-values? P's are the factors of the 4. Plus or minus 1, 2, and 4. Pierce, what are my q values on 23? 1. Very good. So my p over q's are going to be plus or minus all of these over 1, which is just those. Now, I am all in favor of you just using synthetic division. You can plug them in if you really want to, but just remember you're not going to be able to use graphing calculators on your test, so it's probably safer just to start using synthetic. So let's try positive 1 first. 1, negative 2, negative 5, 8, and 4. Drop the 1, multiply, add, multiply, add, multiply, add. Darn, didn't work. So let's try negative 1. Your book sets up like a little chart where it does it like all in one big column, but I have trouble keeping track of stuff like that. So I just like to do it all in individually in their own little space. Drop the 1. Multiply, add, multiply, add, multiply, add. Darn it, still didn't work. Darn. So we'll go to the next number. What's next? Positive 2? Here we go again. 1, negative 2, negative 5, 8, and 4. Drop the 1. Multiply, add, multiply, add, multiply. This might spark. Add and multiply. Did that one work? Yes, we have just factored this into x minus 2 and x cubed minus 5x minus 2. We're still not down to a quadratic though. Now, important step to notice here. We have to keep doing the same method. But we are going to plug numbers into this function now. We're going to take synthetic division of this one. We're no longer going to go back to the original. We've already factored the original into this. So we're going to look for this. Now, another thing to notice. You can have the same root 4 times, couldn't you? Yeah, you could. Remember the ones that touch and the ones that cross? So, when we now try to find one of this, you're going to start with the same one again. Make sure you're not overlooking a double root. So we're going to do the exact same thing, but we're going to do it with our new depressed polynomial. So 2, 1, 0, negative 5, negative 2. Drop the 1, multiply, add, multiply, add, multiply. Darn it, not quite. Alright, so positive 2 didn't work. We don't have to go back and do positive 1 and negative 1. The same one should still work. So what are we going to try next? Negative 2. So let's try negative 2 with 1, 0, negative 5, and negative 2. Drop the 1, multiply, add, hot diggity, we found it. Which means we have now factored this into x minus 2, x plus 2, x squared minus 2x minus 1. I'll give you a second to get caught up and to write all that. And please raise your hand if you have a question about where anything on the board came from. Yes, ma'am. Because remember when we were talking about multiplicity a while back, you could have the same root like 7 times, assuming your degree was that high. I mean, all four of these could have been x plus 2 or x minus 2, x minus 2, x minus 2, x minus 2. So to make sure that it didn't happen again, we just started with that one again. Good question. Well, no, because 1 and negative 1, if they didn't work in this one, they're not going to work in this one. The same ones keep rolling over. Okay, how do I find my last two? Quadratic formula. All right. Negative b plus or minus b squared minus 4ac all over 2a. So that's 2 plus or minus the square root of 8 over 2, 4 plus, or 4 minus the negative 4, 8. What does radical 8 reduce to? 2 square root of 2. Move the end. Oh, I didn't write that very neatly. Which reduces to 1 plus or minus radical 2. Now, that is not a pretty number. That's okay. Just get out your, well, actually, here's the thing. You could just list them like this. Your 3 roots, or excuse me, 4 roots, were 2, negative 2, 1 plus the square root of 2, and 1 minus the square root of 2. That's all 4 of them. You can just leave it like that. Just know that when you were to, if you're not going to have to graph today, but if you were, you would just find the decimals for those by punching them in the calculator. And that one's done. Here are your 4 roots. 2 of them were rational, 2 of them were not. Questions? Any questions about anything you see on this board? This one? Because we already found those. 2 was 1 and negative 2 was 1. We just had to keep them. If it's cubed, yeah. See, if it's cubed, then when you find 1, your depressed polynomial will be a quadratic. But this one started to the 4th. So after we found 1, we weren't to a quadratic function yet. We had to find another one to take it down. Does that make sense? All right. Questions? I'm going to kind of do this section a little out of order. We're going to come back to this slide because it's kind of an independent slide. We're going to go on to the next one. Another trick. This is so simple. People tend to freak out about it. You never have to use this again after today. I won't even put it on your test just because I want to stress how optional this is. I'm going to make it required on your homework because it can be useful. The Descartes rule of signs is just a neat little trick to help you know where to start your search. Because remember how I said some of those P over Q lists could be lengthy. So wouldn't it be nice if there was a way to narrow down our search? Yes. And that's the whole reason the Descartes rule of signs exists. Now, stay with me for a second. Let's look at 33. How many sign changes are occurring? Positive to positive, no sign change. Positive to positive, no sign change. Positive to positive. Were there any sign changes? For every sign change, that's potential positive root you're going to have. Now, how many did we have? 0? Well, if there's 0 positive ones, how many of the 3 does that leave for negative? All 3 of them. So for this one, I would know all of my roots are going to be negative. So I should just start looking at my negative ones when I make my P over Q list. That's the whole purpose of this, just to show you that. It's really only helpful if you get a 0 for one of them. Because if this was like, well, let's look at number 35. Same thing. Let's see. 1 sign change, positive to negative. Negative back to positive is a second sign change. Positive to negative is a third sign change. So how many does that leave for positive? And how many for negative? So once again, it's helpful. Because I know if I ask you to find the root of that, I'll look for my positive ones. The negative ones aren't going to exist. Now, why it works? I don't either. How does it work? I don't know. Descartes is genius.
How did you figure out it was 0 and 3?
Well, did you get the 3 part and the sign changes?
So how many times it's negative.
That's right. Positive to negative, negative to positive, positive to negative. Three
So
sign
if
changes.
it was like positive, positive, it would be 1.
Like 37.
Yeah, let's do 37. Positive to negative, 1. Negative to negative, no change. Negative to negative, no change. Negative to positive, 2. So there are 2 potential positives, and how many does that leave for negatives? So that one, it doesn't even do you any good, because there's an equal chance you'll find a positive or a negative one.
Each positive is negative.
For every change, it's a positive root. And essentially, for the negative, you can just subtract. If there's 4 total and 2 potential positives, you can subtract to get negative. Does that make sense?
Those two numbers have to be equal.
Yeah. Those 2 numbers have to equal the degree. So there were 3 sign changes. There are only 3 total, so that there couldn't have been any negatives. There were no sign changes. There were 3 total, so there had to be 3 negatives. Now, there is one last little thing here that I will say. What if you have an imaginary root? How do you even get an imaginary number? Who can tell me? Square root of a negative number. Square root. Which means you're taking an even root. Which means that every imaginary number has like a twin. Positive and negative I. I mean, not imaginary number. Every imaginary root has a twin. For instance, let's say I asked you to find the roots of this. Okay? So you'd set it equal to 0 and solve. This is just an example, by the way. You take the square root, which is what? Plus or minus I. Every imaginary root is going to come in pairs every time. So one thing they add to this, even though it's really not entirely relevant, is every time you get a number, you decrease by intervals of 2 to take into the account that some of them might have been imaginary. So this could be 3 or 1. This could have been 3 or 1. And these could have both been 2 or 0. You just go down by intervals of 2, taking into the possibility that they could have been imaginary. That's not even relevant to why this is helpful. The whole reason to make it helpful is to find out how many possible there could be. But just so you know, if you come up to look for your answers later to make sure you're doing it right, it's going to list it by intervals of 2. Even if there were 7 possible positives, it would be 7, 5, 3, and 1. All the possible. Keep going down by 2. All you need is the first number. Only thing that will ever prove useful to you. Most people just discard it. They don't even look at it when you have the option to. But for like 33 and 35, it could have saved you time. So the next slide, technically the last slide, even though we're going to go back and look at one, it's the same exact thing you just did 2 slides ago. You're going to list your possible roots, find one that works, divide it out, find the rest of them. It's the same exact thing. Only difference is they say you might use the Descartes rule of signs to make your life easier, to find some that work. So like, let's look for an example here. Doesn't look like, oh yeah, 49. Let's look at 49. If you were to do the Descartes rule of signs, which I'm not going to require, but if you did, you'd notice that there's 1, 2, 3 sign changes, which means there's potentially 3 or 1 positive and 1 negative. So where would you start out? Where would you think you'd have a greater odds of finding one of the roots? Positive. So that helps you. Doesn't look like any of these are going to give you something and 0, which is unfortunate. Those are the best ones. But you don't have to use it right there, but it can help you narrow down your search for your root. Yes, sir.
So the imaginary one, like how it's from the positive.
No, not necessarily. Let's say you had one like, let's go back a slide, like this one, okay? That could mean, let's say we actually solved this problem and our 3 roots were negative 2 and 3i and negative 3i. Imaginary roots don't really have positive negative polarity. That's why they just sort of come grouped together. I know that kind of looks like, hey, that's a positive root, but it's imaginary. It's not really positive or negative.
So we need to either of them are better than 2, but with the eyes.
All potential eyes. That's why they go down by 2. Yeah. It's possible you could have like an x to the 6th function and they could all be imaginary, which is why you have to take it into account. Anyway, that's the whole purpose for the Descartes rule of signs. So this last slide is the literal exact same thing as we had 2 slides ago. You're still finding all the zeros. They just mentioned, hey, you might want to mention the Descartes rule of signs. It might help you. Questions on that? By far the hardest one on that page obviously is going to be 51, because how many here are we going to have to find before we get it down to a quadratic? 3. So you're going to have to find 3 of them, divide them all out, then do the quadratic. Question. There is a possibility, I haven't looked at the answers. If you have one, I don't know if you will or not, I don't remember. It's possible, let's say on 45, you tried all the P over Q's and none of them work. Just put no rational zeros. I don't think that happens, but it might. If none of them work, and you double check your division and everything, just put no rational zeros. And if you don't trust yourself, you can come check my answers.
So, why would, okay, these are zeros. Why would there, does that mean like it's not something that you think?
It could either mean they're all imaginary, or it could mean they're all irrational, so there's no way for you to find one to get started. That's why you put no rational zeros. Saying that there might be some, but we have no tools to find those without using a calculator. Not like calculus and calculator have any kind of root basis or anything. Okay, so we're technically done. I am going to come back and look at this slide because it's kind of different than all the others. This slide, you're just working backwards. What you're doing is they are giving you parts of a function, and they're saying, what was your original function? So you have to work backwards to find that. So they're giving you, we'll look at 25, the number of roots, the degree of your problem. They're actually giving you your roots, and this part I'll talk about in a second. We'll get to it in a minute. So, if there's 3 roots, why have they only listed 2 of them? I'll give you a hint. I gave you a big hint. What's that? No, they've given you all 3. Why didn't they list all 3? Yeah. That's right. Imaginaries come in pairs. So, here's what you're going to do on all of these. You're going to take your list of roots and write them out as binomials. So, that's x minus 1, right, because it's opposite. X minus 5i, and for every imaginary, you have a twin, which is why there's 3, even though they only list 2. And what you're going to do now is just FOIL, and you're just going to get back to your original function. Now, before we start foiling, let me just say, these are our 3 roots. 1, 5i, and negative 5i. What if there had been a 2 out here? Does that change what your roots are? What if this had been a 12, or a 212, or a 1212? None of that changes. You have no idea if there's any kind of number being multiplied by out here. That is the whole reason this part is in here. After you foiled everything out, you're going to use that, and I'll show you how in a second. You're going to use this to find what potential number could have also been out there that did not affect these at all. That way to make your graph all the more accurate, or excuse me, your function all the more accurate. So that's the only reason that last piece is on there. But for right now, let's start foiling. Yeah. Okay, foiling. Let's do the last 2 first. We're going to FOIL the last 2. So x minus 1 times x squared plus 5ix, or 5xi, or however you want to write that, minus 5ix, x squared plus 5ix minus 5ix minus 5i squared. What cancels? That's right. Very good. This is going to be minus 25i squared. What's I squared? Negative 1. So that's minus a negative 25, which is the same as plus 25. Anytime. Anytime. Saying it in a booming voice so that you remember it. Anytime you FOIL 2 imaginary numbers together that are twins, you're always going to get x squared plus a number. Every time. Because that's where it comes from. Yes. Yes. So, keep FOILing. So that's going to give me x cubed minus x squared plus 25x minus 25. And we're almost done. Aren't we almost done, Pierce? Yes, we are almost done. Now, just like what we talked about up here earlier, we don't know what number was here. We need to find that potential number. So you're almost done. But here's what you have to do. You're going to stick some random variable out in front of this. And we have to find what that variable would have been. I mean, not variable, coefficient, that number. So here's how you're going to do it. You're going to plug in -1 for x and -104 for y and solve for a. So -104 equals a times -1 cubed minus -1 squared plus 25 times -1 minus 25. We plug in -1 for x, set it equal to -104, and solve for our phantom coefficient. What do all those numbers add up to? -1 minus 1 is -2. Minus 25 minus 25, is that -52? Pretty sure that's what that is. Almost done. -104 equals -52a. How do I solve for a? Divide. And what's a going to be? 2. A is 2. So all you have left to do is go back and plug that in right here. So that's going to be 2 times x cubed minus x squared plus 25x minus 25, and it'd be better if you distributed it. 2x cubed minus 2x squared plus 50x minus 50. And you're done. This is your finished product. Yay! Excuse me? Yeah. There's an N up here? Oh, that's just your degree. That's telling you what your degree would be, or how many roots you should have. I'm going to make the ones that are like this. That's still an imaginary number, but the foiling's a little rougher. I'm going to make those bonus because I don't really want to focus on this too much. I want to stick with the easier ones with just straight up odds, rather than thinking add or subtract. I'll make those bonus questions if you choose to do them. And there are examples in the book if you want to go back and look at it. So 29 is the only other one on the board that you might actually have. And it's going to work the exact same way. What will my 4 factors be, though? X plus I, X minus I, X plus 3I, and X minus 3I. Yeah.
Now, on the very top of this problem, you got -5 squared.
Yeah.
But on the next one, you got -25 squared.
That's because I squared the 5.
You can
square the other. I'm sorry?
Square the 5 is
I squared them both. I have 5 squared and I squared.
I squared.
Yeah, that's the one step I kind of left out. That's -1, making this -25, minus negative makes it a plus. Other questions about this problem? Not hard, it's just kind of different than anything else we've done, which is why we did it last. Questions? Great, we're done. And it took just about the same amount of time as last block. Things go faster when people play along. Here we go. 28 and 32 are bonus.